So we're going to move on now to the B part of this question, where it's asking for the pH when 20 mils of sodium hydroxide is added to it. So what we're going to do is, again, go to this page here. Let me open up a new one. Okay. So first thing I'm going to do is write down the equation for the reaction between the acid and the base. Now, well, before we even do that, we need to find the moles of the base being added. So the question says 20 mils of sodium hydroxide is added. So moles of sodium hydroxide will be equal to 20.00 mils times 1 liter over 1,000 mils times, now the molarity of course is 0.100 moles per liter. So according to my calculations, this works out to be equal to 2.00 times 10 to the minus 3 moles. All right, so that's in moles of sodium hydroxide. We already know that the moles of hydrochloric acid is equal to 0.100 moles. All right, and then I'm going to write down the equation for the reaction, which is, I'm sorry, not hydrochloric acid, acetic acid, right? I'm just going to use HA, as I said before, to represent it, right? And then I'm going to write down the equation for the reaction between the acetic acid and the sodium hydroxide, typical acid-base reaction, to form sodium acetate plus H2O. So, setting up our ice table, initially, we will have, as far as the hydrochloric acid is concerned, 0.100 moles. For the sodium hydroxide, is going to be 2.00 times 10 to the minus 3 moles. And then over here, you'd have none of this. And again, you don't need to concern yourselves with water. So the change, of course, would be for the sodium hydroxide, because it's a limiting reactant, all of it will react. So the change here would be minus 2.00 times 10 to the minus 3. And because of the stoichiometry here, the change is going to be the same, minus 2.00 times 10 to the minus 3. And also because of the stoichiometry, the change here is going to be plus 2.00 times 10 to the minus 3. Again, we don't need to worry about the water. And then we find out what are the amounts at the end of the reaction. According to my calculations here, the answer would be 0.098. This would be 0, and this would be 2.00 times 10 to the minus 3. So therefore, what this tells us is that at the end of the reaction, there are only two things remaining: acetic acid and sodium acetate. And if you recall, this combination of a weak acid, this is a weak acid, and the conjugate base of the acid constitutes a buffer. And we know of a formula that we can use to calculate the pH of a buffer, and that is Henderson-Hasselbalch equation. All right? So what we need to do is use this equation to find the pH. But before we can do that, we need to find the concentrations of both the HA and the NaA, which means that we need the total volume. What's the total volume? Okay, let me do that down here. Total volume is equal to 1.00 liters, which will be the volume of the sodium hydroxide, of the weak acid, plus the volume of the sodium hydroxide, which is 20.00 mils, which we have to convert to liters. Whoops. So we're going to have 1 liter here over 1,000 mils. And according to my calculations, this works out to be equal to 1.02 liters. All right. So now we can calculate the concentration of each component in this mixture, starting with the HA. That would be equal to the number of moles, 0.098 moles, divided by the volume, which is 1.02 liters. And according to my calculations, that works out to be equal to 0.096 m. and then I do a similar calculation for the NA or just simply A minus, that would be equal to 2.00 times 10 to the minus 3 divided by the volume, which is 1.02 liters. And according to my calculations, that works out to be equal to 1.96 times 10 to the minus 3 M. All right, this should be moles here. All right, so basically all we have to do from here is plug these numbers into the Henderson-Hasselbalch equation. I hope I can find enough space to fit here. Let me just start here. So remember, the equation is pH is equal to pKa plus log of the concentration of A minus divided by concentration of HA. And then we put the numbers in. Now the Ka is given, so to find the pKa, that would be minus log of the Ka, which is 1.80 times 10 to the minus 5, plus log of A minus, which is 1.96 times 10 to the minus 3 M, all divided by 0.096. And when I work this out, the answer I got is 3.04. All right, so that's basically how that problem would be done. And this is in fact the way you'd calculate the pH of any titration process before the equivalence point. All right, okay, so I'm going to stop here. The next question I'm going to do is what is the pH at the equivalence point. All right, okay, until next time.